So one question you might ask yourself is whether electroosmotic, pumping is really a good decision for a particular application. Is it effective? I mean, we know that we can create a velocity, a particular velocity for for a given electric field, but why would I want to do things this way as opposed to using a pump? And is this a good idea? One way we might go about testing that is by calculating the energy dissipation in an electroosmotically driven flow. That can be a little bit tricky. Probably the easiest way I know to do it is to actually just look at the viscous energy dissipation that's going on inside the double layer and try to use that as a measure of how much pumping, because by definition that is the amount of pumping power that is required of the electric field. So we can formulate that pretty easily as a double integral over, essentially an integration over all of the volume of a channel times the viscosity times the rate of strain squared. Now, doing that integration exactly is actually a little bit challenging because we haven't actually explicitly solved for u as a function of y, but because we know that the charge density changes exponentially inside the charge double layer, we suspect that that could be hard to do. However, it's really not too hard to do an order of magnitude analysis here. Because, for example, we know that the change in the velocity is from 0 to u0, so delta u would be u0, and we know that the change in distance in the y direction happens over a distance that is the Debye screening length. So if we just insert those instead of doing the integral, and then, because we know that the limits of integration also go from 0 to the Debye screening length, we can actually sort of calculate the order of magnitude of that dissipative energy rate. Now, let's compare that to the usual pressure-driven flow, so-called Poisson flow. In that flow, the velocity profile is parabolic, meaning that it changes over the course of the entire channel. So whatever average velocity you have in that flow, we know that the changes or the gradient in u in the y direction, in that case, or across the channel, happens over a distance that essentially is the channel length. And so in that case, we can estimate that the dissipative energy is given by mu times something of order u average squared divided by channel length squared. And then if I multiply by the total volume over which the integration happens, you'll get another factor of the channel width times the channel length. So if I compare the two expressions, one for electroosmotic pumping and one for pressure-driven flow, you'll see that they just differ by a factor of the channel length divided by the Debye screening length. Now, typically the Debye screening length is a small number. It's something like, usually measured in nanometers, like 1 nanometer, 10 nanometers, something like that. Whereas, the channel length really depends on what you're doing, right? But I guess the point is that, if you have a millimeter-sized channel, that's probably something like 1,000,000 times bigger than the Debye screening length, meaning that electroosmotic pumping would take something like 1,000,000 times as much energy to use in that scenario. So the conclusion is that electroosmotic pumping is a pretty cool phenomena, but it really only makes sense to use when you have a channel dimension which has approximately the same order of magnitude as the Debye screening length. So in other words, microfluidics and nanofluidics are really the only time when this kind of pumping makes sense.